The last type of inequality that we're going to solve is quadratic inequalities. We solve linear inequalities and compound inequalities first. And so this is our other kind. Linear inequality, first degree, quadratic inequalities for second degree. Now, don't be thrown off by the length of the notes that I wrote you here. Solving quadratic inequalities is actually easy, but you have to follow the steps. You can't make up your own process for this. To solve a quadratic or second degree inequality, you must first change it to an equation and find solutions to the equation. You solve the equation, and those numbers, the solutions to the equation, are called the critical numbers for the inequality. I'll tell you why in just a jiffy. For equations that have two critical numbers, and most quadratic equations do have two solutions, the solutions to the inequality will either lie inside those two critical numbers on a number line or outside those two critical numbers on a number line. You'll put the critical numbers on a number line, and then we will end up either shading the middle or shading the ends. Again, the goal is to find the values that make the inequality true. So here are these steps. Like I said, if you'll follow the steps, you will always get the right answer. You just have to remember that you don't solve quadratic inequalities the same way as you solve linear inequalities. First, you change it to an equation. You solve the equation to find the critical numbers. You put those critical numbers on a number line, and then you use a test point. And your test point can be anything other than your critical numbers. You'll also plot your test point on the number line. If there are integers, whole numbers, between the critical values, then it's usually easiest to pick one of those, one of the integers between the critical values. If you're going to have to pick a fraction, like if your two critical values are 2 and 3, and you don't want to test 2.5, then you can choose your test point to be on the outside of the critical values. You substitute that test point into the original inequality and state whether it makes the original inequality true or false. Now that'll make sense when you see an example. Your shading always represents what makes the inequality true. So if your test point is in the middle and it makes the inequality true, that's where you shade. If your test point is outside the critical values and makes the inequality true, then you shade the ends. You just shade whatever part of the number line contains the values that make the inequality true. If your test point makes the inequality false, don't shade there. For inequalities with two critical numbers, you will either shade the middle or both ends, never just one end or the other. If the inequality is less than or greater than without the equal to, you'll use parentheses on the number line to show that the critical numbers are not included, just like we did with linear inequalities. If the inequality is less than or equal to or greater than or equal to, you will use brackets to show that the critical numbers are included, just like open dots and closed dots. And then finally, you'll write your answer in interval notation. All right, let me show you how easy this is if you follow the steps exactly. Step 1, change the inequality to an equation. So x squared minus 9x is greater than or equal to negative 20. Step 1 says change that to x squared minus 9x equals negative 20. You just changed a quadratic inequality to a quadratic equation, and you're supposed to know already how to solve a quadratic equation. You have to get it in standard form. This one, I'll add 20 to both sides, and then either factor or use the quadratic formula. There are factors of 20 that have a sum of 9, so I'll be able to factor this. It factors into x minus 4 times x minus 5 And the only way this is going to mess up, you're going to mess this up, is if you don't check your factoring. Sure enough, that gives you x squared minus 5x minus 4x plus 20. My factoring's good. And then set each factor equal to 0. And that will give me my two critical numbers. X equals 4, x equals 5. Those are my two critical numbers. Step 3 says put those critical numbers on a number line. So 0, 4, and 5 on a number line. And step 4 says choose a point other than those critical numbers. I can use anything in the world other than those critical numbers. I don't really like plugging 4.5 into this. I'd probably have to use a calculator for that. So I'm just going to pick my test point to be something on either the left end or the right end. It's very easy to plug in 0 for a test point. So I'm going to test x equals 0 back into my original inequality. Now notice here, something that helps me is to write my test point smaller than my two critical numbers. It reminds me that 0 is not one of my critical numbers. It's just my test point. Plug that back into the inequality, and I have 0 squared minus 9 times 0 is greater than or equal to negative 20. That left-hand side simplifies to 0 is greater than or equal to negative 20. Is that true or false? That's definitely true. I'd rather my checking account balance be 0 than negative 20. And that means my test point made the inequality true. And if it's on the left end, then the right end also contains numbers that make my inequality true. You could pick another test point over here if you wanted to. You could test x equals 6. It should make the inequality true also. Now, I'm not really sure why I made a new number line. Normally when I'm doing these problems, I don't make a number line here and a number line here. For some reason I put that in the notes. So I'm just going to transfer my shading down here. Shading represents all the values that make the inequality true. And because this original inequality had greater than or equal to, that includes the critical numbers. And brackets show that the critical numbers are included. Last thing I have to do is write what I have shaded on my number line in interval notation. Forever to the left is negative infinity up to 4, including 4, and from 5 to infinity, including the 5. Very easy to do, but folks make the mistake of forgetting to change this to an equals, and they try to solve it just like a linear inequality. They just bring the greater than straight down. If you bring the greater than straight down all through this process, you're not going to end up with the same thing shaded. You're not going to end up with the correct solution. So changing that inequality to an equation is very important. All right, let's do one more. X squared is greater than 9. Step 1, change that to an equation. Step 2, solve that equation. I could take the square root of both sides as long as I remembered the plus or minus, that would be fine. Or I could subtract 9 from both sides and solve that by factoring. Either one is perfectly okay. Regardless of which of those two methods I use, I'll get the two critical numbers, -3 and +3. So I'm going to put those on a number line. and pick a test point. Any, mini, miny, mo. My test point can be any number in the whole wide world except for -3 and 3. Well, looks like I could use 0 again, but this time 0's in the middle. 0's between -3 and 3. So when I test x equals 0, I'm going to be seeing if the middle contains the solutions. If not, it'll be the ends that contain the solutions again. Testing x equals 0 into the original inequality. 0 squared is greater than 9. That simplifies to 0 is greater than 9. And that's false. So instead of putting a T for true over my test point, I'm going to put an F for false over my test point. My shading is always supposed to represent what makes the inequality true. So if the numbers between -3 and 3 make the inequality false, it's the numbers on both ends that make the inequality true. I could use other test points. For example, if I use -4, I'd have 16 is greater than 9. That's true. If I use +4, I'd have 16 is greater than 9. And that's true. So you can use as many test points as you want to make sure that you have shaded the correct interval. Since what made this inequality true were all the numbers to the left of -3 and to the right of +3, that's where I'm going to shade. And I should have used parentheses on both of those critical numbers because the original inequality did not include the equal to. And all that's left is writing that in interval notation from -infinity to -3, not including the -3, and from 3 to infinity, not including the +3. So linear inequalities are first degree inequalities. You can solve those just like equations, clearing out the fractions, clearing out the parentheses, keeping up with the inequality symbol all the way down, unless you multiply or divide by a negative. That's when you have to reverse the symbol. And that's what you have to remember with linear inequalities. Quadratic or second degree inequalities, you cannot just keep the symbol all the way down. You can't keep the symbol all the way down. You have to follow these steps, change it to an equation, solve the equation, put those critical numbers on a number line, use a test point. It just happened that both of these examples ended up shading the ends, but that's not always going to happen. If my test point here in the middle had made the inequality true, then that's where I would have shaded. All right, that's all you need. And your homework is at the end of the notes. Assignment 7 contains linear inequalities, quadratic inequalities, and 1.4. I think those were radical equations and factorable equations. So you'll have a lot to do on that assignment. Have a great evening, and I'll see you next time.